we are kind of half an hour behind schedule.
Yeah, that's what I was going to say. Should we break for lunch now at 12:30?
We have 6 presentations in the afternoon, so I'm going to do mine fast. How about that? Because otherwise we probably won't have time to cover all the 6 presentations, and they already prepared them. So I'm going to go over my presentation quick. So here's the content of my presentation. I'll talk about some challenges in large cities. Some of you mentioned and asked about already. And then I'm going to talk about the smartphone and using GIS and cloud computing. And then one of the applications we are doing at Queens College. So challenges in large cities, urban canyon effect. Cold start, that means when you first turn on the phone or the GPS logger, it takes a while for it to calculate the distance. And the warm start is, especially in New York City, when you go into subway and then come back up, although the phone and the logger is still on, but it takes time to find its place again after a long gap. So that's a warm start, and it takes a while, and so that's a challenge in big city. And then plus in big cities like New York, you have all kinds of subway, highway, bus routes, and sometimes they cross, but not transferable. So all the connection points needs to be taken into consideration. And plus, traffic congestions can really slow down the bus and car. So in one of our experiments, some of the bus and car were identified as walking because they drove so slow in traffic congestion that it just go to the walking group. So here's kind of a diagram showing you the urban canyon effect, that when the signals from the satellite bounce around buildings, then the calculation of the location and distance becomes inaccurate. And that's why you ended up having points in Hudson River all the time when the person is traveling in Manhattan. And this is one of the experiments we did for NIMTIC, the New York Metropolitan Transportation Council, in 2007-2008. We have 2 types of GPS loggers. One is global set in blue points, and then the eye blue in purple. And the red lines are the streets that I asked my students to walk along. And those are the points recorded by the GPS loggers. So in the Wall Street area, the deviation or the inaccuracy could be substantial. I remember, like in this area, it could be like 60 meters away from the actual street path that the student walk along. And so we also did a little bit with the smartphone and see if the smartphone is doing better. And so the green line is the street that the student walk along, and the red points are the points we got from the smartphone. So it's still not very accurate, so it is a challenge. And this is showing the warm start. The cold start in outer boroughs in New York City is actually not that bad. In Queens or in Brooklyn, it's good, but in Manhattan, it could be bad. In one of our experiments a few years ago, some participants didn't wait in the morning to get a signal before the day, so the whole day we didn't get any data at all because of the cold start. It took longer, and when it's among high buildings, you couldn't get a fix, and so we didn't get any data from the first day. This one shows a test we did for the warm start. So we asked students to, I think, go on the F line, and I think the number 1 or number 8 line. So there were ups and downs going into tunnels and coming back in. And so we asked the students to watch the time, record the time, and then compare it to the time recorded in the GPS loggers. So it shows that pretty much in either the 1 line or the F line, in 2 GPS loggers, there's a 39-second lag when it comes out from the subway. So that's the effect of the warm start. Just want to show you something in Google Earth, that how a student pick up the GPS logger from my office go back home, take the subway to downtown to do the experiment next day, and then take the subway to Midtown to do the experiment, and then take the subway and walk, well, actually, sorry, took the subway in the morning, but walked back across the Brooklyn Bridge home. So this is how you see in a Google Earth. And this is how we'll map up for the F-line, that the green circles shows the data points, but when it goes underground in subway, then we look at any signals, and then when it comes back up again, you will see signals. And this is showing the complexity and of the transportation network in New York City. And we were able to, well, I'll talk about what we did. And this is another challenge, is that usually when you get the GPS data for subway stations, that's what we map as the star. But for one subway station, you actually have many entrances. And so even though you have a subway station here, but when people come out of the subway, they may be actually a couple of blocks away from the subway station already, and then starting to walk away. So it's sometimes difficult to connect the trip to a subway trip when they appear 2 or 3 blocks away from the subway station. So that's a challenge in identifying the mode of the travel. So when we first did the experiment in 2008, 2007, 2008, we used the GPS loggers. At that time, smartphone was not popular. I think there were only 5% of the people were using it. So we chose to use the GPS loggers. But the penetration rate has been increased so much in the past few years. Now, you just saw the previous presentation, 55% of the people are using smartphone now. So it's going to be the future. So I'm listing some of the advantages of using smartphones. I'm going to emphasize one thing is that it connects to the internet, so the data could be transmitted from the smartphone to server, to cloud server. And also has accelerometer readings, so that will help to identify transportation modes underground, especially when you transfer from, say, those commuter rail, and then you don't come out and you connect directly to a subway. You don't get GPS signal at all in that case, but using the accelerometer reading, you could compare the acceleration between the train or the deceleration between the train and the subway, and you could kind of figure out the change of mode in that case. So that's better than GPS loggers without accelerometer information. And also using smartphone, you not only get GPS data from the satellite, you could also get location information from Wi-Fi, from cell tower or hybrid mode. So that's another advantage. This is the result of 2 small surveys we combined in the past. We used GIS algorithm to identify the travel mode. So this is the mode they took, and this is the mode that was identified. And I mentioned before that car mode and bus mode sometimes are identified as walk when there are traffic congestions and become slow. And the rail mode has the lowest success rate because quite often when people come out from New Jersey or from Long Island to Manhattan, they don't really come out. They transfer directly to a subway and then emerge above ground, maybe 20 or 30 blocks away from the train. So it becomes very difficult without the accelerometer information. And when we did this, we used the GPS logger, and we didn't get the accelerometer information at that time. But with the smartphone in the future, we could use that. And this is something I found from the web, showing you the accuracy, that using GPS, the accuracy could be 10 meters, and the availability is 80%, because you may not be able to get 3 or 4 satellites to calculate the location. And the time to first fix, that's actually the cold start, is 65 seconds. But with assisted GPS, you could actually have a higher availability, a lower time to fix. And then if you combine that with Wi-Fi, something called XPS for that company, that the accuracy is 10 meter, the availability is almost 100%, and the co-star is only 1 second. So with smartphone, you could combine Wi-Fi, cell tower information with the GPS to get better result. Advantages of using GIS, we could use connectivities to identify mode transfer. So for example, we built a multimodal transportation network. So it's smart enough that we know at this point, even though you see on the two-dimensional map, you see 2 lines cross, but in reality, if you go into subway stations, you actually have several levels. Sometimes they cross on a 2-dimension, but it doesn't cross or couldn't make the transfer or connection in 3-dimension. So GIS is able to recognize that. And also, we are able to combine the network analysis with proximity analysis. So we were able to use the shortest path to identify some of the travel path when there's no data available, or when it's underground, or when urban canyon is very serious that you don't really get accurate data. And we also use it to identify activity nodes, and we also put it on WebGIS so people can spatially edit their travel information. They say, oh, okay, the GPS or the GIS didn't really identify the right travel mode or right path, and we are going to just fix it in the WebGIS. So this is a table showing the connections among different commuter lines, streets, and subways in our multimodal transportation network. And this is something we experimented, that a student walked from here to there to get a coffee, and then walk along, well, actually took a subway. The subway was above ground, and then go underground, and then above ground again. So using GIS, shortest path, and we limit the shortest path to the areas, I believe it's within 100 meters of those GPS points. We were able to identify 2 trips. And so this is a walk trip, and this is a subway trip. This is using GIS to identify activity nodes that, as Timothy mentioned, that you could get a lot of points when you're stationary in a house or in your workplace. And so we use GIS to identify activity nodes. And this is showing a student buying a lunch and sit in a park, eat lunch, and then walk away. So there are 2 activity nodes here. And we also build a WebGIS that people can actually go and create an account and upload their information, or they could log in and download an app, a phone app, and install their phone so that the information, GPS information, will be sent to our server. And so this is like an overall picture of the WebGIS. This is an example of how you could do spatial editing in the WebGIS, that the GIS algorithm identify the person traveling, well, I think is driving from here and then home, but in reality, is driving here instead of coming here. So the person could actually go online and drag one of the points to here so that it shows the person actually go around that corner to go home. So this kind of spatial editing is possible. We also, our multimodal transportation network was able to combine walking, subway, and driving all in one trip. If you go on Google Map, quite often you have to choose either car or public transit. You cannot mix them together. You cannot drive a little bit and then take the public transit in Google Earth. It doesn't show you the route. But in our multimodal transportation network, we could combine those together. And if the GIS algorithm make a mistake, the WebGIS, you could also change the mode. You could click and select this trip segment and say, well, we didn't go by bus, we went by subway, so we changed the mode and save it in our server. We started to move everything to cloud. in the past few months. So we used the Amazon Cloud too, and we built instances, and then we put it under Elastic, a load balancer, so that when you get more data coming in, it actually adjusts everything itself. And so we put, like, say, for example, here 2 instances under a load balancer. So when there are less traffic, it actually shuts down one of them and uses only one. But when the demand is more, there are more users using it, that actually, put the other instance or 3rd or 4th cloud servers into service. And this is, when you connect to a cloud server, you actually are able to use ArcGIS. And this is the SQL server we have. And this is actually the database for mobile phone. We collect, say, for example, lat long, speed and bearing, and also the XYZ are the accelerometer reading. And then we process it and save it in a geodatabase after GIS, and saving all those nodes and points and trip segments. And so this is, I'm a professor, so I try to put everything into a model. And so in the future, I believe travel survey will be a smartphone travel survey that combines mobile phones, mobile technology, GPS, internet, or actually that connects to cloud computing, and GIS all together to reduce the burden on the participants in the travel survey. This is what we have done so far. As I mentioned, we did a pilot study for NIMTIC, and the research reports were on this website. We also published something in Transportation Research Part A about doing passive travel survey, in which we discuss how to use GIS and GPS to identify travel mode and trip purpose. And then the next one, this one is another publication focused more on the travel mode. And then this is another publication in an ASRI book showing how the commuting and how the GIS and GPS can be used to study people's commuting. And this is the UTRC website that has some of our grant proposals and research reports. And so a recent project we are doing with a professor, 2 professors, one is an environmentalist and one is some expert in public health, is using smartphone app to help people to choose environmentally sustainable and healthy choices. So what we do is we develop the app, and we're going to let the students and staff to download. That will identify the travel mode for that day. And then from each mode, we'll calculate the carbon emission from that trip, and also the carbon avoidance for that trip. So hopefully from those numbers, people see that if I drive alone and not taking public transit, then I'm actually sending more pollutants into the environment. And also it calculates how much calorie you burn and how many fat you burn if you walk and take transit versus if you drive. Drive, usually you go to the garage and then you stop in the parking lot. You don't really walk that much. But taking public transit usually involves some kind of walking. And so we encourage people to take public transit or take those non-fossil fuel transportation modes. And that's achieved by developing such an app called iTransit, that we have a smartphone getting the GPS data, storage it, and then also allow editing through WebGIS, and the information will be stored in cloud computing in databases. And the research will start with a quiz of how much people know about the health and environmental concerns in commuting. And then we are going to have 3 groups. One group is no app. One is using our app that shows you how much you burn calorie and fat each day, and how much you avoid carbon emission each day. And then another group is about carpooling. And so at the end of the research, we are going to do another quiz to see whether, say, during a 6-week time, whether the information we provided in the app help people to choose more environmentally sustainable and healthy travel mode choices. I did pretty good, right? Thank you. Do you have any questions? Okay. I'm just going to answer one question, then the other questions you could ask me during lunchtime. And then we are going to come back, let's say 40. Let's come back at 1:45, okay? I'll answer one question, and then we'll take the lunch break and come back at 1:45. Yes?
Okay, I just had a question regarding the web GIS. So this is actually one who participated in the survey. They actually verified their trip.
Right.
But then, did you have any comparison that how many number of trips and the different purpose, how many trips actually has been changing, and then the number of trips, how many purpose has been changing, that you identify by the algorithm as the one that people before?
We were not able to record those information, but I could give you a rough idea that when we used the GPS logger, our success rate was about 83%. So if there's any changes, I would say roughly about 17%. But we are now using smartphone, so hopefully that will improve because with the assisted GPS and Wi-Fi, the accuracy of the location information will be better, and we also have accelerometer reading. So I don't have the data to answer your question, but this is giving you an idea.
I think that would be really great because now the SRB, they actually do their own step to verify the trip. But then if there's a significant change between the one verification by the participant, the one by on step, if there's much difference, then the legitimacy of the GPS study might be not in a good quality. But,
You two talked over the lunch.
Thank you.
All right, come back at 1:45 after lunch. Thank you.